Hi, and welcome to my talk on topographical effects on granular gravity currents. My name's Johnny Sang. I'm a PhD student at the University of Cambridge, supervised by Stuart Dale and Natalie Vriend, and this work is funded in parts by an EPSRC scholarship. Topographical effects on granular gravity currents. So the sort of thing I'm going to consider in this talk is if you have a gravity current on an inclined surface, inclination theta, and you let it flow over a topographical feature, a bump, let's say, or a weir or a dam, which is described by z equals b. The currents will have a depth averaged velocity u bar, and it's going to have a depth h. So depth is the distance between the free surface and the bump. So the first thing we want to look at is what happens if there's no bump. This case has been studied in great detail, of course, and it's been found that the shear stress, the frictional stress, is just mu times p, where mu is a function of the inertial number. Mu is a coefficient of friction. If we want a steady flow, then we need mu equals tan theta. This determines theta. If we also have a fixed flow rate, then we can determine u bar and h. So u bar and h are functions of theta. We can have a steady flow. Mu takes values between tan theta 1 and tan theta 2, which means that we can have a steady flow if theta lies between theta 1 and theta 2. What I've just described to you is called the mu of I rheology, and it was initially proposed for steady uniform flows, so without bumps, and it was then generalized to 3 dimensions and to time-dependent flows, so to get Navier-Stokes type equations. Then these full equations were depth averaged for shallow flows, and Gray and Edwards came with shallow water-like equations, which I'm going to call shallow sand. Now, the mu of I rheology is very realistic for uniform flows because that's what it was calibrated for. But my question is, what happens when you have a streamwise variation such as this? The reason why we care about this is, firstly, practical, because streamwise variations obstacles might include dams and weirs, which of course are useful in landslide prevention. But more importantly, more fundamentally, it's because we want to have a way of experimentally testing. We want to have a setup where we can make predictions about what mu of I predicts and test them experimentally. So I'll begin by telling you what the shallow sand equations are. They're basically the shallow water equations. So mass balance is the same. You have a momentum balance which is slightly different from shallow water. There's an extra term here for the basal friction drag. There's this term here which is viscosity, or internal dissipations, or internal diffusion of momentum from collisions. And then there's this chi here, which is a shape factor, which tells you about the velocity profile inside the current. Chi is often assumed to be just equal to 1, or just equal to some constant. So if chi equals 1, then we're assuming that the flow is a plug flow. This turns out not to be the case. So for much of the flow, it turns out that the flow profile is a Bagnall profile, and so chi is 1.25 or something. But it turns out that chi is in fact not a constant at all, and I'll show you some DPMs, some numerical simulations of gravity currents where chi is definitely not constant. Okay, so let's consider these in the case of a steady flow. For a steady flow, d by dt is 0, and so q, the flow rate, the mass flux, is constant. And so we can rearrange everything to get an ODE for h, where we write the friction coefficient mu in terms of h rather than in terms of I. So we've just done that. Capital H here is just some material parameter, some depth scale, which is related to the particle diameter. Now, the case that I'm going to focus on right now is if the current has a depth which is scaled according to h, but if the topography varies over a length scale which is L, which is much greater than h, 1 over epsilon times greater than h, If you do all the scaling and you do the non-dimensionalization and you put hats on things and take hats away and rearrange everything, then you get this ODE, where the effect of the slope, the topography, comes in through here. It only comes in through dB by dx and not through b itself. We want to note in particular that dB by dx is order 1 and not order epsilon, even because both b and x are order h over epsilon. So these sort of cancel out. What happens if epsilon is much less than 1? So what happens if this thing is very slowly varying? If this slope is very slowly varying, then the leading order terms are all on the right hand side, and we get an equation for h as a function of s, which we can invert to write h in terms of s. This is the local slope approximation, and what this means is if you have a uniform slope, then the flow, of course, adjusts itself to the natural depth and velocity for that slope. So if you have a slope that's almost uniform but very slowly varying, you'd expect the depths at each point to adjust to the natural depth for that slope. So is this a good approximation? Turns out no. So if you solve the full ODE numerically, then you find that the actual solution doesn't actually match very well with the local slope approximation. It's a bit better on the downstream end of the obstacle, but it's definitely not very good on the upstream end. And in this case, epsilon is on the order of 1 over 15, so that's quite small, but still, there's quite a big error between the approximations. What I've said just now is all about mu of I and shallow sand, but there are several problems with mu of I and shallow sand. Firstly, shallow sand won't work near shocks. What do I mean? So if the dam is steep enough or tall enough, then a shock will propagate backwards, just as in hydrodynamics, a hydraulic jump. And we have this region here which has quite a lot of vertical acceleration or perpendicular acceleration. So shallow sand won't work here. Also, in front of the dam and just downstream of it, we have stagnation and flow separation, and mu of I shouldn't be expected to hold there because the inertial number here is too small and too big. But the interesting thing is, at the bottom of this region, we've got a boundary layer which seems to separate as we go along, as we move into the shock. And so the question is, can mu of I describe this boundary layer and this process of boundary layer separation? To show you more clearly the boundary layer, this is a velocity cross-section of this supercritical region here. And as you can see, there's a boundary layer. Most of the flow is given by a Bagnall profile, but there's this layer of very slow, relatively slow grains down here, whereas in this subcritical layer, there is in a boundary layer, and the whole thing is given by a Bagnall thing. What this means, firstly, is that the shape factor is definitely not constant, because these two profiles are just not the same. And then what I'm interested in now is what I'm working on now is can we describe this boundary layer and this process of separation, boundary layer separation, using the mu of I equations. So what I think we can do is if we scale the mu of I equations properly in this boundary layer, then we can get a Prandtl boundary layer like equation, and then an adverse pressure gradients from the drag comes in, and I want to make arguments similar to Fogner and Stan, which applies for hydrodynamic boundary layers, and that's yeah. So just to very quickly to conclude, firstly, topographical effects are definitely non-local, even in the shallow sand case. But also, the shape factor is not constant, and it seems to depend on whether you're in a supercritical layer or a subcritical layer. And then also the supercritical layer has a slip velocity like this, and the boundary layer does seem to be doing something important at this shock. So its boundary layer separation seems to be important. that's all I have to say. That's all I have time to say. Thanks very much.